So we are discussing chemical bonding. The first and foremost thing everyone must know while dealing with chemical bonding is, first of all, what's a bond? Let me brief you on that. Please understand that you might be having and you might be judgmental about a bond in your previous classes and you might have developed a perception about it. But have a matured thinking. A bond is a force that binds two atoms in a molecule. And whatever happens in chemistry is a function of stability. People do it for what? Stability, right? And stability must always be viewed in thermodynamic terms, that is energy terms, you must understand. And stability and energy are inversely related. So lesser the energy, more is what? Stability. So when two atomic systems are approaching each other to form a molecular system, then I think it is a feasible idea because the molecular system will be having a lower energy. That's why we say atoms combine to form what? Molecule. In terms of energy terms, you must understand the molecular systems seem to be what? More stabler compared to the individual atomic systems. You must understand, right? If that is the case, now what is the perception you must divorce and actually adapt is this, that a bond is basically a force. You give a pause there. A bond is basically nothing but a force, you must understand. And when you say it is a force, in sciences, you have no one force, you must understand, you have several forces. One is an ionic force, right? That's nothing but a non-directional electrostatic force, you must understand. And then the second one is, of course, a covalent force, a metallic force, and an induced force like van der Waals force. So you don't have one force when you consider a bond to be a force that binds two atoms or ions in a molecule. So if bond is a force and force is actually several types in chemistry, similarly you will be having several bonds. And in the first case, we are dealing with ionic bond, and that's nothing but an electrovalent bond, you must understand. So in that process, I was telling you several things, and you might recollect what I told. And what I wanted to tell you today is basically, ionic substances are most of them are solids, right? They're solids, absolutely solids. And we were told in our earlier classes that solids have definite shapes. So you cannot basically discount going ahead without discussing the shapes of these substances. You must understand. Shapes of these ionic solids, right? And remember, when I go to a lab and when I'm preparing an ionic substance, it forms a solid. And solids have a dimension. They have a regular shape, you must understand. And these shapes are not put by me. I am not placing these ions in particular positions and ask them to be there. No, absolutely not. They have actually occupied those positions where they are comfortable. Now, when I say comfortable, what I mean is the positions what they occupy in formation of an ionic solid, they might be experiencing minimum repulsions. Minimum repulsions and maximum attractions. Now, this is the condition for any substance to form a particular shape in solids, right? When a solid is acquiring a particular shape, we are not preparing by our choice. They are actually sitting, whether it's an atoms or ions or whatever, they are sitting in certain positions. And these certain positions are fixed for them and they occupy on their own. And the only condition seems to be that occupancy of these atoms and ions seem to be the most stable of all. So what I mean is they might be experiencing minimum repulsions and maximum attractions. Such a shape would be the most feasible shape for an ionic solid or other solids to attain, you must understand. So people might ask me why a particular substance is having that particular shape or why such a substance is having another particular shape. You must understand. Well, it's not your choice or my choice when you actually prepare this ionic substance in a lab. I think the ions in it or the solute particles, whatever, they occupy certain positions and that positions give them minimum repulsions and maximum attractions. When you have minimum repulsions and maximum attractions, that's where the greatest energy is released. So during the formation of that particular shape, maximum energy is released and that seemed to be the best possible state, best possible shape for that particular solid, you must understand. So what we are trying to tell you is basically ionic substances are solids, and you must understand the fundamental particles in ionic substances are ions. So when you prepare an ionic compound in the laboratory, These ions are occupying certain spaces. These spaces are not your choice and my choice. They occupy on their own. The condition is a common sense. Why they occupy those spaces is that where they experience minimum repulsions and maximum attractions. Minimum repulsions and maximum attractions are basically giving you maximum stability. Maximum stability in the sense most energy is what? Released. So that might be a comfortable position for these ionic solids, you must understand. Now, let us get into details of, what is this ionic solid shapes are, and let us give some technical terms to it. So what you understand is basically what is a lattice. Now, we call this, this is a lattice. Right, the crystalline solid can be called as a lattice, you must understand. These crystalline solids, which are ionic compounds, they form lattices. Lattices. And don't get threatened by these English words, because lattice, I would like to define, repeat, I just wanted to define this. Repeated, this is a repeated with equal distances. This is repeated, regular, regular in the sense equal distances. You're not leaping. So you're actually going in for one stride, that's all. Right? So repeated, regular, three-dimensional, 3D arrangement of ions. It can be ions in the case of what? Ionic solids. But you have covalent solids also. That is also called a lattice. That's also called a lattice. And remember, one thing you must remember, these I'm not preparing. No one is preparing these in the lab. A particular shape of the lattice is got by its own. And I want to repeat this again and again. I want to put this in your mind. These lattices or shapes are not prepared by us, nor you can prepare. Remember, there's the fundamental particles, let it be atoms or ions or whatever, molecules also. Yes, they are occupying that position such that you have minimum repulsions and maximum attractions. Or I can say that they are actually losing maximum energy to form that particular shape of the lattice. You must understand. Neither you are preparing nor I am preparing. They're actually going and sitting when you prepare ionic compounds. You must understand that. Right? So what is a lattice? It's a repeated, regular, three-dimensional arrangement of atoms or what? Ions or even molecules. You must understand. So it's a repeated, regular, three-dimensional arrangement of, it can be an ions, it can be an atoms, it can be what? Molecules. It can be molecules. This is what is basically called lattice. That is a lattice. So it's a repeated, regular, three-dimensional model of arrangements of atoms, molecules or ions in space. In space is called basically space lattice. That's what we call space lattice. Now remember that, in the lattice formation, you have infinite number of atoms, infinite number of what? Molecules, infinite number of ions being repeated regularly in a three-dimensional arrangement. So what happens is, it seems to be huge. It seems to be huge for our understanding. So what we will do is, we will pick up synonymous terms such that we can actually have details of the entire shape of the lattice. Because when you hang on to space lattice, it's infinite, repeated, regular, three-dimensional arrangement of ions, atoms, molecules in space. Infinite. So something speaking in terms of infinite terms is not prudent thing, it's not a wise thing. What we will do is get into something which is simpler ones rather than getting into an infinite arrangements. But we're not deviating from the shapes of the lattice. Remember that it's almost like you're cooking rice. You can't eat and say, or catch the entire rice in your hand and say it has been cooked. We just take one of those and just check it out, and then we arrive at a conclusion that yes, the rice is cooked now, right? So similarly, something what I wanted to say. Otherwise, what we will do is, you understand that there is a wall. There is a wall, and the wall is made up of bricks, right? And when you repeatedly, when you go on repeatedly moving the brick at regular intervals, when you repeatedly do that, right, then it generates the shape of the wall. So what I do is, that's a huge arrangement is wall. So what I do is, I'll take the brick as one unit, the brick as one unit, and then go on repeating it such that you generate the shape of the entire wall. So what we do is, we just divorce it for a moment because it is an infinite arrangement, and it's a we can't it's not good to actually speak in infinite terms. What we will do is, we'll shift from here, and then we will actually go into what is a unit cell. What is a unit cell? So I'm not divorcing lattice. But what I'm doing is, let us speak about the brick of the wall. When you speak about the brick of the wall, then you're speaking of the shape of the wall itself. Because if you have a rectangular brick, the wall will be rectangular. You must understand that. So this is what is the shift what I'm making from lattice to what? Unit cell. So whatever things you will be speaking with respect to the unit cell, we are actually speaking with respect to the lattice. You must understand that. These are not two independent entities. So if I can define it, I think it's well understood. Remember this, what is unit cell is basically, I use these wordings, it is the simplest sample. It is basically the simplest sample. So when you actually see what is the simplest sample of a wall, it's a brick. It's a brick. So unit cell or lattice, both are synonymous. They are synonymous, you must understand. But the only thing what I'm taking is the simplest sample of a lattice, which when repeated at regular intervals or repeated regularly, right, generates the shape of the lattice, shape of the entire lattice. You must understand. From this definition, what I understand is, lattice is nothing but a unit cell, or unit cell is nothing but the lattice. Both are synonymous. The only thing what I'm doing is, I'm just removing the simplest sample from the lattice. And this simplest sample, when moved at regular intervals, generates the shape of the entire lattice. Now, from now onwards, what I will do is, I will divorce the word lattice now, and I will speak only in terms of unit cell, because whatever you are speaking in terms of unit cell, that is nothing but even the lattice, because unit cell is again the simplest sample of the lattice. You must understand that, right? So understand here, lattice. Why are we discussing this first? What are we doing now? What are we doing now is, basically these issues have arisen because the ionic compounds are basically solids, and they are solids, and we were told that solids will have a definite shape. And since ionic solids have ions, right, they are sitting in particular corners in certain positions, which is generating the shape of a lattice. And we want to get into the details of the shapes of the lattice, you must understand. But mind you, I want to warn you that I am not preparing any lattices here. I am not preparing any lattices or unit cells here. The unit cells are already there. The lattice has already been formed. I've just wanted to tell people that how and where the positions are, so that we can fix it off. Except for that, we are not preparing any lattices. You must understand it, right? Now look into here. So if I can rub it before rubbing, what's a lattice? It's a repeated, regular, three-dimensional arrangement of ions, atoms, or molecules. You can have molecular solids, you can have atomic solids, you can have ionic solids. Today we are discussing about ionic solids, right? Since it is an infinite arrangement, what I will do, I will just divorce this and get into a simplest sample, that is nothing but the unit cell. So what is unit cell? Simplest sample of a lattice, which when repeated at regular intervals generates the shape of the entire lattice. So from now onwards, I'm not speaking in lattice terms. We'll stick to what? Unit cell, which is nothing but a simplest sample. Observe carefully now. Now you have certain shapes, ionic solids. Ionic solids basically made up of ions. They just contain ions. You don't have atoms or molecules in it. They just contain ions, right? Now remember, ionic solids will take the shape, shapes like, for example, it is a face-centered cube. Face-centered cube. Or even they take body-centered cube. Now someone is asking me, what is a face-centered cube? What is a body-centered cube? My first prima facie answer would be, this is basically a unit cell. And this is basically a unit cell. And remember, if someone is asking what is FCC and what is a BCC, then understand that FCC and BCC are nothing but what? Unit cells, where some of the ionic solids are sitting in such positions. You and me have not prepared face-centered cube. Neither you and me have prepared this body-centered cube. When you are preparing an ionic solids, they are sitting in that positions. We will detail about that positions. It's as simple as that, right? So remember that this is a unit cell, this is a unit cell. So BCC and FCC. Remember, and you have, please understand, a lattice has, this is a critical point what I'm writing. A lattice has infinite number of unit cells. As I told you, it is the simplest sample of the lattice. So how many unit cells does a lattice have? It might have an infinite number of what? Unit cells. And also I would like to continue to write, unit cells are not isolated. You cannot isolate an unit cell and put it in a hand and just put it as a decorum piece in your room. It cannot be isolated. You must understand. And remember, if they are not isolated and have infinite number of unit cells, then it also implies that a unit cell in a lattice is surrounded by several other unit cells. Now it's a common sense. You must understand. You yourself claim that the lattice has infinite number of unit cells. When you have infinite number of unit cells are not isolated. You're not isolating them. And then a unit cell in a lattice, then it means that if you combine the first and the second and make a reconciliatory statement, then remember that, right, a unit cell is a lattice, in a lattice is surrounded by several other unit cells. Remember that. So when you take this room as one unit cell, it's not an isolated room. You have the other room next to this. You have next to that you have another room. Next to this you have another room. Or you can have top 4 portions above this room also. You must understand. It's not an isolated quantity. It's not an isolated entity. You must understand. Right? So what I'm trying to tell, ionic solids can take the shapes, these shapes, face-centered cubes, body-centered cubes. Now if someone is asking what is an FCC, instead of straight away telling the definition of an FCC, first of all tell him FCC is nothing but a unit cell. It's a unit cell. And remember that the lattice has infinite number of unit cells, and unit cells are not isolated entities. So a unit cell is surrounded by several other unit cells, you must understand, right? So whatever I'm speaking with respect to unit cells, I'm actually speaking for the entire lattice of that particular ionic substance which has taken this shape. Now let us be more specific and discuss about which ionic compounds will actually get into the shapes of what? Face-centered cube, right? Which ionic compounds, and since they are surrounded by several other unit cells, and what are their contributions and all these details, some mathematics involved here. I want you to listen to me carefully. Watch carefully here. Let us take the case of the face-centered cube. The face-centered cube. And let me tell you, this shape is attained by NaCl, sodium chloride. You must understand, the shape of NaCl is basically face-centered cube. And remember, when NaCl is prepared in the lab, well, it's automatically attaining the shape of NaCl. Sorry, face-centered cube. Well, I have not placed them in my choice, and I have not prepared a face-centered cube for NaCl. When NaCl was crystallized, it has taken the shape of what? FCC on its own. And why it has taken the shape of FCC and why not the other shapes? The answer might be, see, you should be answering with common sense sometimes. You have several shapes, but sodium chloride only forms FCC. The initial common sense answer would be that this shape gives them minimum repulsions and maximum attractions. Minimum repulsions and maximum attraction is a condition for stability. So I understand that sodium chloride is only stable when it gets FCC. If it gets BCC or some other shape, I think it's unstable. So that's why it has chosen to be sitting in what? Face-centered cubes. You must understand that. Right? Now let's get into details. The face-centered cube, this shape is attained by NaCl. So I can simply say the unit cell of NaCl is FCC. You must understand. The unit cell, which is the simplest sample of NaCl crystal, is basically what? Face-centered cube. And if I can draw how a face-centered cube looks like, this is how it looks like. Please understand. This is the face-centered cube. Roughly I'm drawing because it's a two-dimensional board. I think you can get a 3D picture. Look into this. This is how the face-centered cube looks like. Right, that is how the cube is looking like. Here is a sodium. Here is a sodium. Here is sodium. Here is sodium. Look into this. Right? And you have 6 faces for the cube. Face-centered. So this is the face. This is the face which I'm looking at. This is the face. Right? And here you have another ion. Right? And the bottom is one face. Bottom is one face. So you have one other face-centered, face-centered. Right? You have this way, this one. This is 3. Right? And you have that way, opposite. This is another face. This is another face, the backside one. Right? This is 1. So you have 4, and you have on the top, you have 1, and at this side, this is one face, this is 1. You must understand. So you have 1, 2, 3, 4, 5, 6, 7, 8. 8 of the ions are occupying the corners. Which ions I would like to tell you? Which ions I'll definitely tell you, but understand how does a face-centered cube look like, right? So that's a face-centered cube, you must understand. On the faces at the center, you have what? An ion occupying. You must understand this, right? So remember that if you take this to be a room, if this is the face, at the center of it, someone is occupying, an ion is occupying it, right? If the top floor, this floor is another face, at the center you have 1. This is one face, you have at the center 1. That face, you have the center 1, right? This face at the center. And the cube has 6 faces. At the centers of it, you have ions occupying. At the same time, understand that if this is the room, that's one corner. Remember that a cube has 8 corners. 8 corners. That's one in this room. This is another. This is another. That's another. That's another. So you actually 4 on the top. So you have total what? Corner points. You must understand. Corner points. So what I will do is remember in general, a unit cell shall have, in general, the unit cell shall have, right, 1, you have corner points, you have face-centered points, And you have the third, even the body-centered points. You must understand. So simple cube will be having corner points, face-centered points, and even you will have your body-centered points. You must understand this, right? And if this is the case, then let us actually see, is this corner points belonging to one unit cell or there are sharing of these corner points? Let us understand this, right? But let me so before I get into the details, here is one more time I just wanted to tell you. The face-centered cube, right, is basically we are discussing this as a unit cell. And this face-centered cube is attained by what? NaCl. And unit cell of NaCl, the shape is what? Face-centered cube. And remember, in general, a unit cell will have corner points, face-centered points, body-centered points. These are the corner points. These are the corner points. These are the face-centered points, you must understand. And the body-centered will be somewhere at the center here. See, somewhere at the center here. It's neither at the face, neither at this face, neither at the corner, somewhere at this center. This center. Somewhere here. You must understand that. Right? So let us get into details and apply this whole thing to what? NaCl, and judge, right, how many ions are there in a particular what? Unit cell. Now observe carefully. Let us have a better understanding of what we are telling. Let's have a better understanding. Let's get into complete details. Let's have a complete details of unit cell, that is the face-centered cube. Face-centered cube, you must understand. And this is nothing but NaCl. You must understand this. Let us have the complete details of the face-centered cube, that is NaCl. Now, what is my worry? What do you mean by the details? What do you mean by the details? Remember, this is the issue. This is the issue basically. The issue is a unit cell is not isolated, rather surrounded by, that is nothing but the FCC, right? I can tell you that the sodium ions are at the edges, are basically at the edges, right? They are occupying edges. I didn't place them. They are automatically occupying the edges. And remember, a cube will be having 12 edges. It will be having 12 edges. If you want me to count, I can, right? If you take this bottom floor on which you are sitting or standing, right, you have 4 edges, 1, 2, 3, and 4, right? And similarly, if you take the side wall of your ears, I think you will have again 1, 2, 3, and 4. Like that, you can actually see 12 edges in a cube. 12 edges in a cube, you must understand. You have 12 edges, right? So, sodium is at the edge centers. Edge centers, right? And also the sodium ion is at the body-centered. Body-centered point, you must understand. So sodium ions are occupying the edge centers and they are occupying even at the body centers, you must understand. And then coming to chlorine ions are at corners, are at corner points, and even Cl minus is at face-centered points. You must understand this. And remember, it is not my choice. I didn't place them in those edge centers or body-centered points. You must understand this, right? So if I can draw the diagram for you, it looks like this. Watch carefully. Watch carefully here. Look into this. This is the cube. That is a cube. That is a cube, right? And what I'm doing is Na plus is an empty circle if you actually see, or a darkened circle. Cl minus would be an empty circle. Then if I can place this Na plus at the edge centers, let us put them. This is the edge center. This is one edge at the center. 2, 3, and 4, and 5, and 6, and 7, and 8, and 9, and 10, and 11, and 12. You must understand. So you have 12 edges. At the edge centers, the sodium ions are occupying. Look into this. Look into this. These darkened circles are sodiums. These darkened circles are sodiums. You must understand. Right? This is the darkened circles. These are the sodiums. You must understand. Well, I didn't place them at the edges. I didn't place them at the edges, right? They are occupying the edges on their own such that they are comfortable, because that's where they are giving minimum repulsions and maximum attractions. You must understand. And also the sodiums are at the body center. That is somewhere at the center. It doesn't touch that face, touch this face or something. It's basically at the center. It's not touching any edges. You must understand. So somewhere here is again the sodium. You must understand. This is the sodiums. So in face-centered cube, this is how the sodiums have occupied at the center of the edges, and a cube has 12 edges. You must understand, right? And then coming to chlorine ions, so they are at the corner points. Now chlorine ions are empty circles. So if I can draw an empty circle, this is 1 chlorine, 2 chlorine, 3 chlorine, 4 chlorine, 5 chlorine, 6 chlorine, 7, and 8. You have 8 corner points. 8 corner points. 1, 2, 3, 4, 5, 6, 7, and 8. Right? On the flooring you have what? 4. And on the ceiling you have 4. So you have total 8 corner points. You must understand. Right? So those are the chlorines. The empty circles are what? Chlorines. Coming to the other position, that is nothing but, face-centered points. And a cube will be having 6 faces. 6 faces. This is one face to my side. So here is 1 chlorine. Opposite to that, you have another face, that is 1 chlorine. And on the top, the ceiling, you have one other. And at the bottom, you have one other, right? And to this side, you have one other. And to the opposite side, you have one other. So you can see here 6 face-centered. 1, 2, 3, 4, 5, and 6. And remember, this is one face. Opposite to that, you have one face. Here is one face. Top one face, and to my side is one face, and to the back side is another face. You must understand. So you have 6 face-centered points. You must understand here. So be clear, since it's a 2-dimensional photograph, I think you can check a 3D photograph for better understanding. But I think you are clear. Sodium ions are at the edges. These are the edges. Right? That is an edge. That's an edge. At the center of that, you have sodium ions. You must understand. Right? And the sodium ion is even placed at the center. This is body centered. It's not touching anyone. Right? And the chlorine ions are occupying the corners. You have 8 corners. So if I can write it, edge centers are basically, so if I can calculate it, right? But before we get into calculation, have a clear idea. Remember, Na plus are at the edge centers. Na plus is at the body centered, Cl minus is at the corner points, and Cl minus is even at the face centered cubes. You must understand. Now the issue is a unit cell is not isolated. You are not taking that in your hand and put on your hand like this and put it as a decorum piece. You can't do that. You cannot do that. So what you're supposed to do is, this one is basically surrounded by several other unit cells. It's not an isolated entity. So the points what we are showing, a corner point does not belong to it completely. The face-centered point does not belong to it. The edge-centered point does not belong to it completely. The face-centered point does not belong to it completely. Right? They are all shared things, because this room is not isolated. I have another room next to it. And opposite to that, you have another room. And next to that, you have another room. So you have 4 portions here. And on the top, you have another 4 portions. So total 8 rooms. 8 rooms. And each point is not belonging to this particular unit cell. It's shared by 8 people. So there is sharing of every point which is shown, except for one point, that is body-centered. This is not shared. This is somewhere inside that room. This is not shared. The body-centered point is not shared. You must understand. Right? So what we will do is, we'll make a calculation. What calculation? Let me be very clear. Let's calculate number of sodium ions, comma, number of Cl minus ions in a unit cell. Let us calculate that, right? So what I'll do is, as we know, the Na plus is occupying two positions. One is the edge center and at the body center. Well, a cube will be having 12 edges. You must be knowing the cube will be having 12 edges. Let us consider one edge and check it out how many. If you have a point somewhere at the edge, that is the edge of the cube, and if you have a point at the center of the edge, it is actually shared by 4 people. You can actually see here, right? This room, next to that is another room, on the top one more room, and the next to that you have. So 4 portions are actually sharing the edge centered point. You must understand. 4 rooms. Look into this edge, this particular edge. You can actually see this is the edge. That is the edge you have, right? And at the center you have what? An edge-centered point. So that edge-centered belongs to this room. The next room, on the top you have another room. On this you have another room. So 4 people are sharing that edge-centered points, and total you have 12 edges. So each point is shared by 4 people. So for one room, it's only contributing 1 by 4. You must understand. That point only contributes only 1/4 because it is shared by 4 people. 4 people. If one idli is shared by 4 people, then you must understand one cake is shared by 4 people, then each fellow will get only 1/4 of it. So you have 12 edges and it is only contributing 1 by 4. So you have only total 3 Na plus ions per unit cell. You must understand. 3 Na plus ions is the total contribution by the edge-centered points. Now coming to body-centered, you have only one body-centered point. One body-centered, because this centered cannot be shared by anyone. This is at the center. You can't be shared by one. So this entire Na plus belongs to this particular room, right? So that it's a total contribution. So that is 1 Na plus by this. So total Na plus per unit cell is nothing but 3 plus 1, which is 4. Per unit cell. It is 4 Na plus per unit cell. Now coming to Cl minus, look into this. Cl minus, they are occupying what? Face-centered, and they even occupy corner points. You must understand. They are occupying face-centered and corner points. Now look into a face. This is a face. This is a face. This is the center. You have a point, chlorine occupying. This wall is common to 2 rooms. It's common to 2 rooms. A wall can be common to only 2 rooms, right? So the point is actually shared by 2 rooms. So if a cake is shared by 2 people, its contribution is only half. And you have 6 faces like that. So face-centered are 6 faces and its contribution is only half. So you have 3 Cl minus per unit cell. You must understand, right? And you have corner points. Let's come to this corner point. This is the corner point of the board. This is the corner point, right? This does not belong to this particular room. No, this is actually shared by this room, next room, then opposite to that you have another room, next to that you have another room. So this corner point is shared by 4 rooms at the bottom. Not only that, if you put 4 portions on the top, so 4 rooms on the top, 4 rooms at the bottom, right, is the contribution that the corner point is shared by 8 rooms. 8 rooms. Understand that. 8 rooms. Because look at this. That corner point, wherever you're sitting, look into that corner point. That does not belong to this room as a whole. Next to that you have another room. Opposite to that you have another room. Next to this you have another room. So 4 people, the corner point is what? Common. Not only that, if you put 4 portions on the top, so total 8 rooms are actually sharing that. You must understand. So corner points are basically 8 corners. And if a cake is shared by 8 people, the contribution is only 1 by 8. So 8 corners contribution is 1 by 8. That is only 1 Cl minus per unit cell. So total Cl minus per unit cell is basically 3 plus 1, that is 4. So if I can calculate total Na plus comma Cl minus per unit cell, then it is 4 Na plus comma 4 Cl minus. You must understand 4, in fact 4, I call this to be ion pairs per what? Unit cell. Now why all this discussion is happening? Because I have written the issue is the unit cell is surrounded by what? Several other unit cells. You must understand that. Right? We will get into a numerical calculation for this, and we will do that. Right?